Hello to everyone, I'm Luca from the Politecnico di Torino, and today I'm here to present our work. The main motivation that led to this work is that the existing identification benchmarks are limited in size and variety, and even if this is not true, they covered a limited time and/or space. The contribution was twofold. The first is the development of a model for a damaged object identification task, and the second one is the design of a semi-automatic pipeline that simulates different types of damage over an object. The pipeline is composed of two main phases: the model preparation that must be performed mostly manually, and it is done once for each new object. The second one is an automatic script that generates a set of rendered images of the object before and after damage. The dataset split was made at the level of BBICYCles and model in order to assess the generalization abilities of the deep neural networks between EDs and across models. The stress test uses only unseen models, whereas the validation set contains both seen and unseen models. Also, a dataset of real photos of the bikes was collected for benchmarking and domain adaptation purpose. The model is based on the state-of-the-art visual transformer-based model for vehicle identification. On top of that, some additional components were added: a multi-label damage detection branch, a multi-combined loss, a multitask diversion mechanism was added because the real images couldn't be used for the re-identification task, and domain adaptation technique to reduce the diversity between synthetic and real images. It is possible to see the architecture in detail here. First, the learnable patch and position embeddings are input to a transformer encoder along with non-visual information such as camera or viewpoint that is encoded by the side information embedding module. All patches are reorganized into different groups by the jigsaw patch module, which then inputs each group to a shared transformer layer to extract local features. The damage detection branch is a multi-label classifier with 7 output heads, while the global branch learns the re-identification task. Now I'm going to present our findings. According to experimental results, Transray 3D performs better than the single task identification architectures, demonstrating how the damage detection task helps the identification task. On the other hand, damage detection improves on both real and synthetic images when used in a single task environment. Domain adaptation techniques improve performance on the damage detection task over the baseline, but not over the supervised technique. Instead, considering that the identification task only evaluates performance on synthetic images, domain adaptation slightly halves the performance on this task. Overall, the damage detection task generalizes well to the previously unseen models. However, in the re-identification task, both TransRayD and the re-ranking transformer exhibit a modest performance drop when trying to generalize to completely new bike model. In the end, we analyzed how the background affected the re-identification and the damage detection performance. In particular, we compared 3 background alternatives. On the damage detection task, all transfers achieved similar result. There is ample opportunity for future expansion in various directions given the novelty of the task. For example, re-identification should improve in generalization to unseen models, or the proposed pipeline could be used to investigate other tasks. In conclusion, we propose a novel task of damaged object identification and a benchmark dataset which contains paired images of the same bike with and without damages. As a baseline, we propose Transray 3D, multitask transformer-based architectures for joint damage detection and identification. Thank you for your attention.